Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be solving this interesting problem, number of ways to arrive at a destination. Till now we have been doing problems like shortest path and all these stuff, but this is pretty interesting and it's different from the all the standard problems. So you're in a city that consists of n intersection numbered from 0 to n minus 1, which means that it's a zero based indexing graph and it's an undirected graph. Okay, and these are definition of graphs. So you're given an integer n and 2D integer where they have stated the roads. Basically, there's a road between u and v, and in order to travel from u to v or v to u, you're taking time. This means that whatever it is, you want to know in how many ways you can travel from. They've given the source as 0 and the destination as n minus 1. So to figure out in how many ways can you reach from 0 to n minus 1 in the shortest amount of time is what the question does ask you. So if you look at this particular example and n is 7, so the source will be 0 and the destination will be 6. Okay, so if you travel from 0 to 6 directly, it's taking you 7, and this is the shortest that you can do. You can try out all of the paths: 0, 4, 6, 5 and 2, again 7. If you try something like 0, 1, 2, 5, 6, 0, 1, 2, 5, 6, you can see 2, 3, 1, 1. That is again 7. And there is again 0, 1, 3, 5, 6. 0, 1, 3, 5, 6. So that's 1, 3, 1, 1, which is, sorry, 2, 3, 1, 1, which is again 7. So all of these four paths are taking 7. There is one other path as well, which is this, which is going to take you 2, 3, 3, which is 8. But that's not what we require. We require the number of shortest paths. In short, the question is the number of shortest paths is what they're asking, not the shortest path. How many paths are there which are shortest is what the question states. What is the first intuition that comes to your mind when you think of finding the number of shortest paths? It is definitely something like if this is a source and the destination is this, and we are reaching via various paths. And if I can figure out the shortest distance, assume the shortest distance to be x. This is also taking x. This is also taking x in total. This is also taking x. And assume this takes x plus 5. So x, 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 3 paths. 1, 2, 3. So I can say the number of times someone reaches the destination with the shortest path is what I'll count. That can be an intuition. That is actually wrong. That might work for examples which are something like this. If I give you an example, something like this, a very, very straightforward example where I take unit distance on every edge weight. So I'll be like, okay, 1, 2. So the distance over here assigned, minimum distance assigned is 2. So you'll be like, okay, 2. Again, someone came by 2. Again, someone came by 2. So 3 times 2 did arrive. So I can say it's 3 times. What happened? Yeah. 3 times we assigned or we ended up having 2. But this is completely wrong. Let me give you an example to prove it, why it is wrong. Now assume I take this particular example. Okay. Now you will be thinking, okay, there's one guy coming from here. There's one guy coming from here. There's one guy coming from here. So you might think we'll count this as path 1, path 2, path 3. So apparently if you follow this logic, you'll get 3 paths. Because once you'll come from this node, once you'll come from this node, once you'll come from this node. So there can be 3 instances. But that is actually wrong. Why? Because one path might be this, which is taking 3, right? One path might be this, which is taking 3. Something to observe. The first path went via this, and the second path also went via this. Got it? Again, this might be a path which is again taking 3. Again, this might be a path which is again taking 3. So can I say that if I just count one path from here, that is wrong? Because to reach here, there were 2 paths, right? So can I say to reach here, there were 2 paths? To reach here, there was just one path. To reach here, there was just one path. So can I say, if I'm taking this, I have to actually count 2 instead of counting 1. Then 1, 1. So I can say 4 instead of 3. So you just do not say that, okay, I came from here, I came from here, I came from here, and everyone was like distance 3. Because this path also gave me 3, this also gave me 3, this also gave me 3. And there were 3 guys who gave me 3. So I cannot say 3 paths. No, because this, he himself is arriving from 2 different positions or 2 different ways. So if he himself is arriving from 2 different ways, we just cannot count it as one. So the logic of saying that the number of times I get the shortest path to the destination is actually wrong. You have to trace back how many times did every node. If this arrived 2, if this could have been 10, this could have been 100. You just have to add all of these guys who are arriving. So if you're arriving at a node, if you're arriving at a particular node via various, assume node 1, node 2, node 3, and everyone is giving you the shortest distance. Then you say ways of node will be, it won't be like 1, 1, 1. No, it will be ways I arrived at this, which is ways of node 1 plus the ways I arrived at the second node. Someone would have arrived over here. Have to add that up. Got it? And plus the ways someone would have arrived at the node 3. And I summarize that up. And that is what the total ways will be. Similarly, in order to find this guy, the number of times these guys will be arriving. Similarly, in order to find the ways for this one. So I hope you have understood the intuition, what I was trying to convey. Just in case you did not an issue. I'll be taking this complex example and trying to explain you the intuition as well as the dry run so that the algorithm or the logic gets into your head straight away. So as usual, we will be applying the Dijkstra's algorithm. So what is the initial configuration? Priority queue and a distance. But this time we need to count the ways as well. So an additional ways array will be defined. So let's check out the initial configuration. So initially we will have a priority queue which is going to store a distance and a node as similar to the Dijkstra's algorithm. We will have a distance array. We know the source is 0. So 0 will be assigned to 0 because when we start off, the distance is always 0. Now we have an additional ways. Yes, the number of ways in which you can reach a particular node. Now remember, this is your source node. So what I say is, hey, I know one thing. There's only one way where you can start from the source. So let's keep it as 1. And everyone else has not been reached yet. Let's put a 0 saying you haven't been reached. Your number of ways as of now is 0. Okay. Now, initially, distance 0, source node 0 is what we will put into the priority queue. First iteration says I'm at 0. I'm at the node 0. Where can I go from 0? Where can I go from 0 is my question. So from 0, you can go to 1, you can actually go to 2, you can go to 3, and you can go to 4. And these are the distances you will take. I'm assuming you are now very comfortable with Dijkstra. So if you go to 1, this will be added. And if you go to 1 plus 1, so the distance will be 1. So you'll see that the 1 is having infinite. So you'll go and update this to 1. And you'll say 1 in order to reach 1. And can I say, if you're coming from here, this guy was taking one way, and you're coming from here, this guy will also take one way in order to reach via a distance of 1. Can I say this? I can. So I'll update this to 1 as well. Fine, I've updated everything. Now, can I go to 2? I can. And the distance will be 2. So go and update that to 2. I can go with a distance of 2 to 2. And the ways will be 1. Because from 0 was to reach 0, there was one way. And if you're going via this, it's just a one way to reach here, right? Next, you can definitely go to 3, which is taking 1. So I can say 3 is taking 1. So 1 comma 3 is what you'll put into the minimum heap data structure. Okay. Now what I will do is I'll also update the ways to be 1. Because if you're coming from the source, again to 3, it will be one way. Similarly to 4, the distance will be 2. So go and update the distance to 2, the ways to 1. and I can say distance 2 to node 4. So I can say the iteration for 0 is over. Pretty simple. The priority queue says who will be at the top, the minimum, and the minimum is 1 comma 1. So take out 1 comma 1. I'm saying 1 in order to reach the node 1. From 1, where can you go? You can go back to 0, but that's going to take a plus. Like if you try to go back to 0, that will take a plus 1 and it will make a total distance of 2, which you will not consider because you're reaching at 0 already. So not to be considered. From 1, you can also go to 5. So if you decide to go to 5, that will it'll take a distance of 2, make a total distance of 3, which is better than infinite. So you go and say, okay, I can reach at a better distance 3. So 3 comma 5 is what I'll take to reach. Now what will be the number of ways? Now 1 says I can reach in one way. I just have one way. So you will also 5 will also be one way, right? So I'll say, okay, 5, you can also keep 1 to yourself. Perfect. Done. What will be the next smaller guy among all of these? 1 comma 3. So I'll be like, okay, 1 and I will have a node 3. 1 and I'll have a node 3. So on node 3, where am I? Node 3, right? Where can I go? I can go to 5. Very, very important. Very, very, very important. Okay. So I can go to node 5. That will take a distance of 2. Correct? So the total distance will be 3. Carefully observe something. Very, very carefully observe something. Distance is taking as 3, right? Now I see at node 5, it's already taking a distance of 3. So it's not the first time. It is not the first time that I am reaching with a minimal distance because 3 I've already reached. I'm again reaching via another path with the same minimal distance. So thereby, I can say one more way. I can. And so in order to reach 3, how many ways did I take? 1. So this will also be one way. So I'll say 5. Increase your number of ways to 2. In order to reach 5 with a distance 3, I have taken something like this. But will you put this into the priority queue? Is there a point of going and putting 3 comma 5 again when it is already there? No. But I need to count my ways because one more way I got. Got it? Perfect. Amazing. Super. Next, where can 3 go? 3 can go to 7 and 6. Let's try to go to 7. So if 3 tries to go to 7, 7 is infinite. So the distance taken will be plus 3 and the total distance will be 4. 4 ways 1. 4 comma 7 is what you'll put into the priority queue. It can also try to go to 6. If it tries to go to 6, distance will be plus 2. Total distance 3. First time, one way, distance 3, node 6. Perfect. Right? So I'll just quickly, very simple because this one was one way, 1 and 3. And this was one way, 1 and 2. And since you reached 3 via one path, this will also be one path and this will also be one path. So done. Let's erase this. I've erased this. What's the next thing? You'll figure out who, sorry, by the way, 1 comma 3 is done. So erase it. Now, who is the next guy out of this, which is the smallest? 2 comma 2, take a 2 comma 2. Distance of 2 to a node 2. Now, from 2, where can you go? You can go back to 0. Yes, with a 2, you can go back. But if you go back to 0 with a distance of 2, total distance of 4, not to be considered because it's not the minimum. Okay, where can you go? You can go to 5. Very, very important again. If you go to 5, you take another 1, make a total distance of 3, but 5 says, hey, I've already taken 3. So I'm one more way in which I can reach 5. I'm one more way in which I can reach 5 with the same minimal distance. So I'll say, no need to put this into the priority queue. No need. Just go and say to update this to one more way. So 3 ways now. Wow, amazing. Next, I'll be like, node 2, can you go somewhere else? He's like, no. So I'm done with node 2. Perfect. So node 2 is done. So 2 comma 2 is done. Next will be 2 comma 4. Okay, where can 4 go? Let's quickly analyze this. 4 can go to 6. 4 can go to 6. So let's see. If I try to go to 6, I'll take another 1, which will make a total distance of 3. But wait. 6 has already taken a distance of 3. One more way, guys, with a distance 3. One more way with a guy distance 3. So I'll just increase this to 2. No need to put into the priority queue. 4 could have gone back to 0, but not to be considered. Okay. So 2 comma 4 is also done. Who's the next guy? 3 comma 6 or 3 comma 5? 3 comma 5. Yes. Distance of 3 to a node 5. Distance of 3 to a node 5. Very, very, very important. Please stay focused because this is where you understand the crux of the algorithm. Okay. So you're reaching 5 by taking a distance 3. 5 can go to 1, but not to be considered. Can go to 1, not to be considered. Can go to 3, not to be considered because none of them will be lesser than these guys. None of them will be lesser. So there's only one way which will be lesser, which is if you go to node 8, and that will be a total distance of 4. It is infinite 4, but will you just put 1 or will you put 3? Think. Very obvious. You know, in order to reach 5, the number of ways were 3. 5 could be reached in 3 ways. So there are 3 paths which are associated with 5. So can I say that even if you reach 8 for the first time with a distance of 4, but you actually reached for 3 times? Understood? Because there might be one way from here, but actually this is 3. Combination, right? So I can say, okay, I will just take whatever ways 5 has, which is 3. Perfect. I get excited, but yeah, that's how I teach. So I can say as of now, 4 comma 8 is what I can reach. So done. So I can say this is done. So thereby 3 comma 5 is done. Amazing. Next, which is the smallest, 3 comma 6. 3 comma 6. Now 6 says, where can I go? Let's stand at 6. Cannot go to 3, not it will not give short. Cannot go to 4, it will not give short. Can go to 8. Again, important. Can go to 8 by taking a distance of 4. Can go to 8, right? 3 plus 1 gives a 4. But 8 says, hey, wait, I've already reached with a distance of 4. You again reached via some other path which takes the same distance. Thereby, I will go say, hey, 6. How many times did you? How many paths were there for you? He says 2, which is very obvious. I'll be like, let's take 2 and add it to myself. I have 5 paths now, which reaches at 8 with a 4 distance. It's not just 2, it's 5 because you took into account these guys as well. Got it? So, do I take 4 and 8 and put it? No, because they've already reached. I do not take and put it. Perfect. Next, I have taken 6 into account, so this is done. Next will be 4 comma 7. So 4 comma 7. Now we have reached 7 with a distance of 4. Now I can go to 8 with a plus 1, makes it a total distance 5. But I'm like, it's 5. It's more than this. No need. Ignored. Similarly, you can go ahead with doing 4 comma 8, you'll not get anything. At the end of the day, 8 says I can reach in 5 ways. 8 says I can reach in 5 ways. Got it? Very simple. Very, very simple. So I hope the intuition was clear as well as the entire dry run because that is where the crux of the algorithm is. Now we will try to code this up. So what are we given? We are given the number of rows actually. So we need to create the graph. So we know the graph will be storing adjacent nodes and the edge weight. So create the graph. N will suffice because it's a 1 based indexing arrays. So go ahead to all the rows and say, hey rows, can you just go ahead? I'll just take it this side. Yeah. IT of 0 dot push back of IT of 1, which is the first adjacent node, comma ID of 2, which is the weight. Similarly, can I say I'll copy paste the same thing because it's an undirected graph and I'll make it 0 and I'll make it 1 and 0. So graph is ready. Now we need to apply Dijkstra's algorithm. So if you remember the Dijkstra's algorithm, it required priority queue. So let's quickly declare a priority queue. This is how I can declare a priority queue of pairs because I'm going to store distance and node. Next is very, very simple. I'll take a distance and I'll say, okay, n comma 1 in n, everyone with infinity. And I'll take a ways of n comma 0. What after this we need to initialize. So can I say distance of the source, which is 0 is 0? Can I say the ways in which you reach the uh, starting node is just one? And can I say pq dot push will always contain distance 0 and the node 0? Done. Now I can go ahead and iterate in the queue. So simple Dijkstra, go and iterate in the queue. Next I can say auto of it, or I can just maybe write something like int dis equal to pq dot top dot first, and I can say int node equal to pq dot top second, and I can go ahead and say pq dot pop. Perfect. Next I can go ahead and iterate on the graph, and I can say the adjacency node is this, and I can see the adjacency weight is this. Correct. Now what is the next thing? The next thing I need to check is if the distance taken till now, the edge weight is lesser than distance of adjacency node. That means this is the first time I'm arriving. This is the first time I am coming with this short distance. It's not the repeated occurrence. It's the first time I'm coming. So can I say the way, sorry, let's first update the distance, then I'll talk about the ways. Will be dis plus ed weight, and I can say pq. Can you go ahead and put dis plus ed weight comma adjacency node? I can, right? What about the ways? Can I say in order to reach the adjacency node, I came via node. I came via node. So whatever node was, I'll just take it. I'll not add it because it's the first time I'm arriving with such a short path. So I'll just copy it. But what if we are having a same path as the shortest path already arrived? Then I'll say, okay, no need to update the distance because this is the same shortest distance I've already got. So I'll be like, ways of adjacency node, can you please take ways, like can you just go ahead and take adjacency node plus ways of node, which will be like, yes, because whatever ways you have reached, I'll just take you because that's my job. Once you have done this, can I say this is what you'll return because that's what they need, n minus 1, because that's the destination. But wait, will you submit this? No, because they're saying that please return the answer modulo 10 to the power 9 plus 7. So maybe you can keep something like integer 1e9 plus 7. Okay, now whenever you use modulo, just make sure you do a modulo whenever you do an operation like a plus or a multiplication. Just do over there, and over here also you can just go ahead and return it. I think this much should be more than enough. And now let's quickly compile and see if it is working fine. Wow, errorless code at one go. I'm proud of myself. Let's quickly submit this and see. Okay, so works fine. Now it's time to discuss the time complexity. So we're using a very simple Dijkstra's algorithm. So I can say it's E log V because we're using something like this, but this doesn't adds up to the time complexity. It adds up big of n to the space, but not to the time. Got it? So guys, I hope you were able to understand the entire intuition, the extreme dry run, and now the code. So just in case you did, please make sure you like this video. And if you're new to our channel, what are you waiting for? Hit that subscribe button right away, and please let me know in comments, did you like the energy of this video or not? And if you haven't checked out our DP series and the HD sheet, the links are in the description. With this, I'll be wrapping up this video. Let's meet in some other video. Till then, bye bye. Take care.